Tracy, can you please confirm? Am I still audible? If yes, please give me a sign so that I can start. The slides.
Yes, we can hear you and see the slides.
Perfect. Okay. So many thanks. Welcome to this conference. And today I will try to talk about the use of Ethernet TSN in industrial and automotive sectors. As a background, I have done my PhD in the industrial sector of Bosch in the industrial automation. With focus on the use of Ethernet time-sensitive networking in industrial as well as in automotive sectors. And I want to give some ideas how can we profit out of the somehow old history of Ethernet use in IT and operational technology or industrial automation, and how can we gain out of these experiences and the mechanisms. So the outline is as follows. A little bit about the Ethernet evolution history from office, from the IT world to the industrial automation, then to the automotive. Why is Ethernet actually so attractive for automotive, and what is IEEE standardizations and enhancements to the standard IEEE 800.1a the so-called time-sensitive networking, as well as the use cases of TSN in industrial and automotive sectors. We'll try to answer also the question, how can automotive sector profit out of the industrial history, and what are the most important Ethernet key challenges in automotive before summarizing the talk or the speech. So let's start first with the Ethernet evolution history. Ethernet is actually widely used, not only in automotive, but actually started using since the 70s in the IT networks. The typical requirements here are the high bandwidth. It goes up to even 100 gigabits per second. Ethernet ports or Ethernet cables with the port RJ45. We know it actually even from home, especially in the 90s or the early 2000s without VLAN or WLAN. We were always using the cable to simply plug and play new devices to the home network. And therefore, scalability is a big word actually for the IT networks, as well as the reliability and the security. But these are much more important than timing constraints. It means once we send an email from home or from work, then we don't expect that this email is coming after exactly 100 microsecond or half second or 1 second. It doesn't matter. What matters is that the email is coming from the receiver, from the sender to the receiver at the end of the day. But this matters where? In the industrial sector and in the automotive sectors. So here we talk about the so-called operational technology network. Here are the requirements typically about deterministic communication. Means we need to have always an upper bound end-to-end delay. The jitter should be low in the microseconds range, and even in some use cases in the industrial applications, it should be even in nanoseconds range. Scalability is as important also, but at the end of the day, the minimum latency matters really. Reliability and determinism are here quite important as well. So we see that Ethernet is actually not only used in IT networks, but also in wide ranges here. And here, maybe the most important advantages are the continuous development of Ethernet since 1972 until now. We see a lot of enhancements, a lot of development groups that are still existing and extending with covering more and more signals, more and more applications and use cases. This is thanks to multiple benefits of Ethernet, such as the high bandwidth. Yeah, here we talk about up to 100 gigabits per second, which is quite important for storage applications in IT, but also in industrial and automotive sectors, like in ADAS or highly autonomous driving. Ethernet offers also huge frame capacity with the so-called jumbo frames. It goes up to 9,000 bytes, yeah, in one single frame, especially in storage, as I mentioned, and it offers a high scalability and wide use case from IT automation with a huge community. Yeah. One of the most important also motivations why to use Ethernet is the seamless infrastructure. What we mean here is actually that in the plant, we use Ethernet with the same RJ45 like in the office, and an engineer can actually monitor and controls the plant from its office, yeah, using more or less the same protocols. Nevertheless, this wasn't the case as Ethernet has been introduced for the first time in the 70s, especially with a lot of collision and so on, with the CSMA protocol or communication mechanism. And therefore, maybe we go to the next slide and understand how was the Ethernet evolution over the time. So here we talk about two kinds of Ethernet, actually. The IEEE standard conform Ethernet, as well as the modified Ethernet. So Ethernet, as at the beginning, it has been introduced, as we said, in the early 70s. And there we talked about the so-called shared Ethernet. Then switched Ethernet has been introduced, AVB and TSN. AVB stands for audio video bridging. It's a group that thought, yeah, let's further develop Ethernet to cover audio and video signals. And TSN is the same group, but it has expanded and extended the signals to cover also hard real-time control frames. So if we compare them from the devices and the infrastructure, shared Ethernet uses bus hubs and repeaters, and therefore it was half duplex, and that led to a lot of collisions. The bandwidth was by around 10 megabits per second, so it's not much more than CAN or FlexRay. But with the introduction of the switch Ethernet in the 90s, everything changed, and Ethernet became very, very important and very lucrative and interesting for applications outside of the office or the IT. That was by the introduction of the switches. Yeah, with the switches we can build virtual networks. Yeah, and we have full duplex, so that the collision is now completely avoided. Not only that, but also the bandwidth and the throughput have been increased from 10 megabits to up to 1 gigabit and more, of course. But this was not enough for having for using Ethernet for certain applications, as I mentioned, for audio and video signal processing and transmission. And therefore, IEEE introduced the AVB group, which introduced new mechanisms like clock synchronization with 1588 and IEEE 800.1 AS, but also the credit-based JPA to reserve some bandwidth and stream reservation. That are the most important AVB communication mechanisms. With TSN, the evolution has been really dramatically increased, yeah, by introducing some new time-aware JPA, frame preemption, time synchronization, redundancy policing, and so on. And we will go through them in a while. The point is, at the beginning of the 2000s, the industry or the industrial sector, especially the automation, they have seen in the Ethernet a huge potential, and therefore they started already modifying Ethernet, since AVB and TSN mechanisms by that time were not available. And here we talk about the so-called modified Ethernet, which is not standard conform. Yeah. We see a lot of protocols that are used in avionic like AFDX, in automotive like time-triggered Ethernet introduced by TTTech, and in the industrial Ethernet world, we see the most famous protocols, let's say, and the most experienced protocols, like Siakos, like EtherCAT, Profinet. We all heard about such protocols. The most important thing here in the industry, the factory automation compared to the automotive networks is a little bit more complex, more different. Here we see in certain applications up to 200 nodes in one single network, yeah, and sometimes they are cascaded into a line or a ring topology, which is quite unfamiliar in automotive small networks. We talk also about very, very small cycle times, sometimes below 100 microseconds even. This clock synchronization here is highly important for printing machines, for example, or controlling some robotics in movement. And here we expect far below clock synchronization or clock accuracy far below 1 microsecond range, in the nanosecond range, which is given actually by TSN. So in the early 2000s, the industry has experienced a patent course, if we want to call it. Yeah, a lot of companies like Bosch, like Beckhoff, Siemens, they were in a course to specify new communication mechanisms and to introduce to the industrial sector new protocols like Profinet, Siakos, and EtherCAT. And introducing new mechanisms. Most of the important mechanisms are, for example, introducing the so-called cut-through or fast forwarding mechanism instead of store and forward. So the frames are not completely stored in the single hops or switches and then forwarded like we know it in the automotive domain or in the IT domain. Here, in order to reduce the forwarding delay within a single hop, since we have a cascaded line of up to 200 devices, as we mentioned, the cut-through means from reading the first 10 or 14 bytes, depending on the protocol, the frame can be identified as it can be forwarded, and I know exactly as a slave which field I need to consume, and I don't need to record the whole data. But also the time-triggered communication by introducing time slot and reserving them for only protecting the most important frames and to forward them on time. But now we may ask ourselves, why is Ethernet then attractive for automotive? Yeah, after we have seen that automation has learned a lot from the IT, and can we use actually what we have seen? So to recapitulate, in the industrial automation, now we have a high availability of know-how, of specifications, of even chips, yeah, that are introduced from semiconductors to big companies like Bosch, Rexroth, Beckhoff, Schneider Electric, and so on, and Siemens for use in the automation. This reduces, of course, the costs and thus the prices on the market and the availability. Increases the availability. It increases for Industry 4.0, for example, a flat network without a huge hierarchy by using the same protocols in the IT and in the OT. And sustainable solution is always a key success for a sector. Yeah? Each sector, also the automotive, wants to rely on a standard solution which is given by Ethernet. So what are the most important use cases? Yeah, we can that we can talk that are now that they were not imaginable in the past, and now they are feasible. For example, changing the architecture and introducing new architecture like zonal or zone-oriented architecture, thanks to the strong backbone of Ethernet, but also supporting service-oriented architecture. This allows, for example, a dynamic configuration of the ECUs or of the gateway and the vehicle computers instead of having static configuration. So the automotive applications, they can profit actually very well from the established Ethernet in the IT. And the IT, as we mentioned, the focus is on the high bandwidth, the security, and the robustness. In the industrial automation, we can profit out of the real-time communication. Here we see actually the evolution. It's famous for the automotive sector, how the evolution of the E-architecture is established, and that Ethernet played a strong role as a backbone on the high level. So we differentiate, of course, between three main architectures, like we see it from Bosch. The domain concentration and the fusion, domain fusion that are existing nowadays, yeah, already. Here we see a lot of domains, for example, ADAS or ADDA, autonomous driving, driver assistance, powertrain, safety, infotainment. They are all like closed networks, sub-networks, let's say, in the in-vehicle network. They are distributed and they communicate over a single gateway, let's say, with not a lot of intelligence behind. Here, the most important thing to mention maybe is that the system is highly complex. We have quite complex wiring harness, and the configuration is a static configuration. Therefore, we thought about, and the whole market thought about maybe reducing this complexity by making first step is by fusing the domain. For example, we can fuse, let's say, an domain A with domain B, so that only a single computer or a single ECU is controlling the two closed subnetworks. And last but not least, with the introduction of centralized vehicle computers and central gateways, we think even about geographically distributing the zones to talk about front zone, rear zone, and central zone. Where in each zone there is a computer which is exactly controlling the devices behind or below. Thanks to such architecture, we can reduce up to 20% less components. Nowadays, we see over in the domain concentration here, or the distributed domain, we see over 100 ECU devices that they can be reduced here, but therefore the complexity of the device itself and the intelligence of the device will increase a little bit. One of the benefits is also the wiring harness that can be reduced, and the weight that reduces, of course, the weight and the complexity. Now, maybe if we go to TSN and see how can we profit out of it. So what is TSN? As we mentioned, TSN stands for time-sensitive networking. It's a group of standardization, IEEE standard conform, that was in the past called AVB, and now by supporting more signals like control signals and introducing new communication mechanisms, they were renamed to TSN. The three pillars, let's say, of TSN are synchronization, clock synchronization, of course, deterministic communication, and path management and security. For clock synchronization, TSN introduced or refined, let's say, the IEEE.1 AS from AVB, and it renamed it to AS-REV for revision. in the determinism, TSN introduces a lot of deterministic approaches, like the time-aware shaper, TAS, which offers a time-triggered communication by reserving time slots. Also, the frame preemption transmission, yeah, .1 QVU. It's a very important mechanisms that, combined with 1 gigabit Ethernet communication, it can reach actually the effect of time-aware shaper with 100 Mbit or 10 Mbit. In the path management, we have resource reservation, .1 QCC, seamless redundancy, but also per stream filtering and policing. Let's go maybe in the clock synchronization, which is the most important aspect currently in the automotive. So from the industrial sector, if I go back from the industrial sector, more or less all of them are considered to be supported. But in the automotive, the focus is currently on the clock synchronization. How does this work? Actually, it's very easy, the architecture, let's say. To simplify it, we have an ordinary clock and boundary clocks that can be also so-called time gateway, if we are introducing gateway with supporting multiple buses. So the ordinary clock, it can be either a master or a slave, and it has a single port. A boundary clock is a switch, for example. It's some kind of a device that is receiving and forwarding certain GPTP frames. So a boundary clock can only be a slave at a time. It cannot have multiple masters at a time. So the data will be distributed from the ordinary clock. It will be corrected on the ordinary slaves, let's say. So AUTOSAR is actually using IEEE 802.1as as a reference for clock synchronization, and it is in use currently in automotive. Yeah, we see a lot of products supporting IEEE 800.1as and even 1588 since years. Yeah, for example, in infotainment. But today is also with the introduction of ADAS and so on, we see that .1as is also highly in use. Limitations from AUTOSAR, it's not completely 100%, let's say, standard conform. It's a little bit modifying it and making it a little bit simpler by not using the BMCA. It's an algorithm to choose between multiple devices which has the highest accuracy, and that should be the best master. But also the path delay requests and response are overjumped, let's say, and not supported. .1as is a very good standard that is not only supporting hardware timestamping with high accuracy, but also software timestamping if the device is not having that high accuracy, let's say. One of the most important aspects in industrial sectors, for example, is the configurable cycle time. Yeah, the standard is introducing at least eight sync frames can be exchanged between master and slave per second, but this can be increased up to 128 synchronization frames per second. And we see here that the accuracy timeout, let's say, or the time delay duration until the network is synchronous below 1 microsecond, it can be highly reduced if we increase the number of synchronization frames, but this might take some of the bandwidth. Therefore, with 1 gigabit, it shouldn't be a problem at all. So what are the use cases of TSN Ethernet in industrial automation, but also in automotive sectors? Typical requirements of industrial applications are can be divided in soft real-time applications and hard real-time applications. Soft real-time applications, we can talk about the so-called condition monitoring and process automation. And the hard real-time, especially packaging machines, printing machines, machine tools, and so on. The artifacts here for comparing all of the aspects are cycle time in milliseconds, They are between even 100 microseconds until 1 milliseconds. It depends on the number of devices, the synchronization accuracy, and the payload supported. And we see here how big is the difference to the automotive sector. Yeah, in the automotive, we don't talk about 100 devices or even 1,000 devices in a single closed network. Yeah, we talk about maximum 10 devices that are maybe communicating over Ethernet in a single network. The payload, it is definitely comparable. For example, in diagnostic, we see, of course, that we support most of the time 1,500 byte frames. But the cycle times are also not so small like in the industry. For example, sometimes we see configurable 37 or 40 microseconds for multiple devices. So how are the use cases in the automotive sectors? Here we talk about gateway development using Ethernet as a communication backbone. Here is the focus on data synchronization. Thanks to the high throughput and bandwidth, the jitter can be reduced and the delays can be also highly reduced, especially by supporting .1 QBV, time-aware shaper, and frame preemption if required. It depends, of course, on the complexity and the applications. Sorry. One of the most important applications also are ADDA or autonomous driving driver assistance applications, where we see a huge data exchange. Yeah? Because we are using and supporting sometimes in some projects over 20 cameras, especially in a single car. Here we require also sensor fusion, for example, between two radars, front radar left and right. They need to fuse the data in order to measure the distance to objects on the road. But also what we see is during the development of the cars, we require for level 4 and 5 of autonomy, high data acquisition and recording. It goes up to 100 gigabit per second, yeah, for measurement purposes, yeah, and this is due to the high amount of data introduced by LiDAR, radar, and especially cameras and video streams. And here we see that the high clock synchronization is a must-have. That can be also used by TSN AVP-REV protocol. Now is the question, how can automotive sector profit from industrial automation? As we mentioned, TSN and Ethernet especially is having a wide use in the in multiple sectors, IT and OT. Therefore, the semiconductors are aiming to introduce chips that can be used simultaneously for automotive and IT and industrial sectors. This would introduce a huge or mass production of TSN chips if TSN is used in the automotive, especially the automotive sector, where the mass production is can be supported. We have seen already during my PhD in 2014, I've seen the early prototypes of Ethernet TSN from IT companies like Cisco and others, Digitech, but also in the from companies like Bosch, Rexroth, and Siemens and so on. So early TSN prototypes were already available even by Renesas and Intel, yeah, since 2015. So we can imagine using certain products now in the automotive sector. The use of certain communication mechanisms from industrial automation is also highly attractive. like cut-through instead of store and forward, but for special use cases in the automotive. Cut-through, as we mentioned, the frame doesn't need to be completely stored and then forward, especially if the frame is by 1500 byte. So we can only read this specific field out of 20 bytes, let's say, out of 1500, and quickly fast forwarding the frame. But also supporting ring topologies and line topologies and path control for data redundancy. So we are not making the devices redundant, but we are making the path redundant, which may reduce the costs and increase simultaneously the robustness of the network. Last but not least is also the new mechanisms like transmission interruption with .1 QPU and time slot reservation with .1 QPV, which I guess still not supported by every company since it introduces some complexity for the configuration of the overall network, but it definitely reduces the end-to-end delay, and I'm quite curious to see how it would be developing, especially with the introduction of highly autonomous driving level 5 and full autonomous driving. So next chapter, what are the most important Ethernet key challenges in automotive? So we see the in-vehicle multi-gigabit transmission of data with upcoming ADDA applications for measurement purposes, but also the electromagnetic compatibility, the robustness and the reliability, especially in the noisy automotive environment. Low cost, low weight of the wiring harness are required to support all of the devices in so-called what we call today smart cars or data center on wheels, due to the high amount of data. And last but not least, a common network configuration, as I mentioned, is one of the most biggest challenges for using TSN Ethernet in not only automotive, but especially in the automotive and the industrial automation sectors. So to summarize, Ethernet is a widely used communication technology. Since maybe 50 years, it has been introduced already in the 70s. It's not only used in office or IT, but also in automation and in automotive sector. Standard technologies and standard conform mechanisms are always a safe investment for each sector. Continuous development and enhancement to the IEEE standard specifications are a big support for using Ethernet in automotive. We don't talk about whether we use Ethernet actually today in the automotive or not, or in the in-vehicle network or not. Ethernet has been established since several years. I remember already having seen a lot of use cases in 2014 already for Ethernet AVB, especially for audio and video transmission synchronization. And that proves, that Ethernet, even in automotive, is in use since several years, and this will definitely increase in the future. The question remains only which sub-standards or enhancements from the huge list of TSN, they are already by 11, I guess, which one are the most important and which one can be used. Last but not least, the synergies between automotive, IT, and industrial sectors are required, and we need to somehow create synergies and working groups between the three worlds so that we can profit the best from the further development of Ethernet and accelerating its use in the automotive sector. So, and now we come to the end of the presentation. and I am open for questions.